Alright, so we'll continue with surface tension. We have understood what is surface tension. Now, before we go to the next topic, that is surface energy, I will just give you two use cases. Alright, so let us say there was a ring, there is a ring, okay, and it was dipped in some liquid. So there is liquid all over now, okay, and let us say there was a thread here. Okay, there was a thread here. The ring is dipped in a liquid, some liquid. You're dipping it, so it's coated with liquid now, and there is a thread here. Okay, now if you puncture here, that is, if you puncture at A, how do you think the thread will move? This is covered by some soap, for example. Okay, you're dipping it in a soap solution. The entire ring gets coated with liquid now, and there is a thread here somewhere which is not actually bound as such. Okay, and there is a point A which is on this side. If you puncture this region anywhere, how will the thread move? That's the question. Alright, now what happens is, let us see. Okay, now if you puncture it, what is going to happen? There is no liquid here because everything is gone now. Okay, so there is nothing here. If you puncture, you're putting a puncture here, then what happens to this? Now this acts like a surface molecule. Do you agree? Earlier, the whatever the liquid molecules here were bulk because there was liquid here. Now they act as surface molecules, and when they act as surface molecules, there is force which is pulling them inside. I told you, correct? Sidewards and downwards. There will be force on the surface here also, but that force is not enough to be pulled because this is a rigid surface. So when they pull it inside, what will be the shape? The shape will be something like this. So it will become concave towards A. Concave towards A. Towards A, it goes in. So puncture, it becomes concave towards A. This is one conceptual question. Similarly, if I have to put a needle on water, remember I told you if you carefully place a needle, it will start floating, alright, because of surface tension. Gently if you put, you have to find what is the maximum mass of the needle that you can put in water, okay, in general. Maximum mass of the needle you are supposed to find if you have to gently place them in water so that it can float with the help of surface tension. Okay, now I want you to visualize this. Okay, so what happens when you're trying to put a needle in water? Okay, does it create a kind of a depression? Now imagine this is a needle. When you place it gently, there is a kind of depression created, like, right? It is something like this. And now can you see there are two surfaces here created? One is, the depression is, one is on this side. I'll just show it to you like this. This is my needle. One surface is created here and one more surface created on the other side of the needle, because this is something which is getting stuck here. One side, the second side. So I have my needle here. Alright. So this is one surface. This is my surface 1. This side is my surface 2. There are two surfaces. And if you look at the front view like this, okay, it looks like a U here, front view. If I put it like this, the depression looks like a U, this part. I'm just zooming it here. So the weight of the needle will be acting downwards and the pull will be acting upwards. This is the pull in two directions because, it's like, it's a U. I told you this, correct? So now, remember we had discussed this. What is the force? Force is S into L. The force with which it is getting pulled is nothing but S into L, and force is mg here. Okay, S is 2S because I have two surfaces, 1 and 2, 2S into L. So what will be m? Because they have asked me the mass, 2 into S into L by G. So if I know the length of the needle, whatever it is, length of the needle, if I know the surface tension of water, which is very, very small, there is a fixed value, but it is very minuscule because it depends on the length and the force. Okay, so of course, if you know the length, if you know the surface tension of water, G, you can calculate the mass. Okay, so these are two conceptual questions. Now we will go to another concept which is called as the surface energy. Okay, remember I told you the bulk molecules, they are at a less energy. They are stable. Why? Because they are forming many bonds. When they form many bonds with everyone, less energy. There is no force on them. Very less energy, very stable in life. But the surface molecules, because they are not able to form bonds with the top molecules, they have more energy. Because they are not able to form more bonds, they are not able to form more bonds, so no energy is released out. They have more energy because they are not giving out energy, because there are no much bonds in comparison with the bond molecules. So I can say surface molecules have more energy in comparison with the bulk molecules. So this extra energy which is possessed by the surface molecules is what we call as surface energy. Surface here represents surface molecules. Energy which is little higher in comparison with the bulk molecules, that energy possessed by the surface molecules is what we call as surface energy. And there is one the derivation, the potential energy of the surface energy is given as U is equal to S into A, where S is the surface tension, A is the area. Okay, so it goes something like this. It's there in your textbook also. Imagine a U-shaped frame and there is liquid here. You're putting the frame in the liquid, alright, and there is one movable frame. So this is your movable frame. I can slide it like this. This is movable, alright. So there is a movable frame. Now let us say I'm moving it this side. So the force is acting in this side, and let us say for example the displacement when I moved is dx. Dx is the displacement. This length is L. Alright, I repeat, this L is moved by a distance x. It is moved by a distance x. So now tell me what will be the area here. Area here will be in this area covered when I move the force, correct? The area covered is nothing but L into dx, because this is a rectangle now, correct? So what will be the, and what, because I'll be having two areas. Are we able to visualize this concept of two areas? Okay, now there is a wire. I will just rotate it like this and put it in water. So this, it will be now in this term. So this is that moving frame. I will move it like this or like this. So if I'm moving it like this, this is the displacement which I'm telling you about. Okay. Now when you move it like this, do you agree there are two surfaces, one below and one on top? Imagine this is the wire frame. One is the surface below, one is the surface on top. Since there are two areas, I need to multiply it by 2. So it is 2 into L into dx. And what is work done? Work done is to change the area. Okay, work done to change area. That is from L to this much, or to move basically, right? So whatever work you are doing, that will be stored as the surface potential energy. And if we calculate the work done to change the area, that will be stored. See, whenever we talk about potential energy, is the stored energy. So if I in case of a spring, you've studied it in work power energy. If you're trying to pull the spring, your mechanical energy is saved as the potential energy of the spring. Same thing here. You are doing some work in changing the area. That work will be stored as surface potential energy. And what is work done? That is du, change in potential energy. Work done is force, which is that external force which you are applying. So I'll write it as Ex. Displacement is dx. W is F into S. And this is du. Okay. And what is F? F here will be, hold on. F is the force. In terms of surface tension, it will be 2 into S into L. Force is 2SL. The basics of surface tension. Into dx is equal to du. Okay, now what is LDX? LDX is area. So what do I get? 2 into LDX rather. 2 into L into dx is area. So work is force into displacement. That is what I have. And instead of force, I have written 2SL. And if I combine 2L and dx, I get area. So that is how I get. And if I integrate on both sides, this is my dA. That is what I get, small area. So if I integrate on both sides, this is dA. Alright. If I integrate on both sides from 0 to u, from 0 to a, I will be getting u is equal to S into a. S is the constant, dA, summation is nothing but the total area. So this is the expression to calculate the energy of the surface molecules. Alright, now whenever you are trying to blow a bubble, you might have done blowing a bubble. So what happens? The bubble, it becomes bigger. So basically your energy is getting converted, or you are using your internal energy to actually increase the radius of the bubble. Alright, so I have one question on that. Maybe we can quickly do that. Yes. So calculate the work done to increase bubble size, or increase the bubble to 2r. Let us say there was a bubble of r, small r. Okay, let us say there is a bubble of small r. You are blowing it and then you are making it a bigger bubble of radius 2r. So, what is the work done here? Work done to increase the bubble from r to 2r. Okay, now, just now you studied, work done is nothing but stored as potential energy. And what will be the change in potential energy? UF. There would have already the system would have had its potential energy. You are doing work. So overall your work is converted and stored as extra potential energy. So that is what I meant by change in potential energy. So it is UF minus UI. What is UF? Let us write it. UF is the final. What is final? You just now derived an expression for U. U is SA. Okay, surface tension is constant. This will be area final. What will be area final? This is area of a sphere. So it is 4 pi 2r square. But remember, I told you it has, even if you consider a sphere, it has got two surfaces. One here, one externally. External surface area of a sphere, internal surface. Okay, so it has got, that's why I need to multiply by 2 here. So this is going to be 4 16 to the 32 pi r square. 32 pi r square into s, and what will be u initial? Again it is a initial, so it is s into 4 pi r square. R is just r here, into 2 because surface 1, surface 2. Okay, so this is going to be 8 pi r square into s. So now if you take the difference, 32 minus 8, you are going to get 24 s pi r square. This is the work done to increase the size of the bubble from R to 2R. Alright. Now there are a couple of questions. You can just go through my notes. Alright. Let us now understand the concept of excess pressure. Very important. Okay. Excess pressure. Okay. Now imagine I have a surface like this. Let us say there are 2 points P1 and P2. Both will be equal pressure. But if I have a curved surface like this side is concave surface. You know this. This side is concave surface. Sorry, convex surface. Where will the pressure be more? Obviously, the pressure will be more here. It's trying to push here. Correct? So, if I say this is P1 and this is P2, P1 is greater than P2 here. Pressure at the concave surface is always greater than the pressure at the convex surface. So if you talk about spheres or something, a ring and all that, it will have two surfaces, one concave and one convex. And whenever you have such shapes, the concave surface will have a greater pressure. This difference in pressure is what we call as excess pressure. So how can we define excess pressure? Excess pressure is nothing but, in this case it is P1 minus P2 or P concave minus P convex. This is the external pressure. Alright. Now, what is happening here, actually I'll tell you. And this actually tells you another, it gives you another insight to why it is trying to become spherical. Alright. Now, anything, what happens, there is inside pressure, because it is concave, pressure is more here, and here outside pressure, if you think of any spherical liquid, mercury or anything, okay, because it is concave, the pressure is more here. Because it is convex, the pressure is less. That is nothing but an external pressure, if you talk about a water drop or anything. Alright. Now, because of surface tension, what happens? The external pressure, it tries to minimize its surface area, correct? So that is the reason it is trying to become minimal, at least the minimum spherical position it will try to achieve. Alright. So now what you need to also know here is, this is something very important what I'm going to say. Excess pressure, we have to calculate the formula for excess pressure for 3 cases. Okay. First is the water drop. Okay. In the second case, you have a liquid somewhere and there is an air bubble. This is my air bubble inside a liquid. What is air bubble? You could have seen when something is boiling and all that, you can see there is air here. Okay, there is no liquid here, there is air. And the third one is a soap bubble. There is a difference. Okay, I'll tell you what is the difference, and this is where people go wrong. This is a soap bubble. Okay, what is the meaning of soap bubble? There is air here, okay, and there is a thin film of soap. So there is soap here, okay, there is soap here, and outside also there is air. Now, I hope this is clear. Water droplet, what is water droplet? There is water here, liquid, and there is air outside. Okay, air bubble in a liquid, inside air, external liquid. Soap bubble, air inside, liquid or the soap film in between, and air outside. So what will be the pressure in this case? Pressure is directly given. This is just no derivation, you just have to remember this. It is 2S by R here. Here also it is 2S by R. Okay, in general, excess pressure, we are talking about excess pressure, the difference between concave and convex pressure on the concave and convex sides. But only here it will be 4S by R. So whenever the question is asking about soap bubble, don't write 2S by R for excess pressure, 4S. Why? Because now it has got two surfaces. There is air and soap. Soap and air, there is one internal surface. Soap and air, there is one external surface. It is so thin that we consider the surfaces to be of the same area. So 4 pi r square, 4 pi r square. Okay, so I hope it is clear. So be very careful. A water droplet or any liquid droplet, air bubble 2S by R, soap bubble it will be 4S by R. Alright. Now, yeah, I think I will just do one question, and angle of contact in capillary rise, I will do it in another video. Okay, so yes. Alright, let us say there is this diagram like this. This question they might give you, so I'm just drawing it. Okay, look at that. There are two soap bubbles. This is your soap bubble, and this is also your soap bubble. Okay, with different radii. What will happen? Okay, they are connected by a tube like this. Okay, eventually what will happen? Will there be no change, or this becomes smaller, this also becomes smaller? What is happening in general? Let us try to understand this. Okay, now both are soap bubbles. So what will be the external pressure which is inside? I will write it as internal pressure, or let me write it. P excess or excess pressure is given as, for a soap bubble it is 4S by R. And what is P excess? It is P internal minus P external, that is 4S by R. Or what is the internal pressure? Pressure inside. It is P external plus 4S by R. Now what is the difference between these two bubbles? R is going to be lesser. Okay, so let us consider what happens when R increases. When R increases, I will write it here, when R increases, 4S by R decreases. And if 4S by R decreases, P internal will decrease. Correct? So P internal will decrease. So that means for the bigger bubble where R is more, P internal is less here, P internal is more here. If the pressure is more here, what is going to happen if the internal pressure is more here? Air will flow because there is more pressure. Now you know, more pressure, air will flow from here to here. So what is happening? This will become smaller and smaller. So after final picture, if you want to see, this will become smaller and this bubble would have become bigger. It is like this. Poor becomes poorer, rich becomes richer. Small bubbles becomes even more smaller, bigger bubble becomes even more bigger. And the simple reason, what is it? Nothing but excess pressure. Whenever you have more radius, it means that the internal pressure is less there because of this. Higher the radius, less is the internal pressure, more is the internal pressure. To equalize pressure, force, and that's the reason this becomes smaller and this becomes bigger. Yes? Alright.